All right, so we're going to get into polynomial arithmetic in this video. First, some helpful notational convention is instead of writing our polynomials as follows, like in the last video, we'll opt to write them sort of ambiguously as sum on Ri t to the I with the understanding. So instead of this, we write the second one. With the understanding that Rk is 0 for Rn, for n bigger than or equal to k. Rk is 0 for k bigger than or equal to n. There we go. That is, we don't want to consider series, which is where you allow non-zero coefficients of arbitrarily high degree. We want a polynomial. So what's true about a polynomial? Well, it's a sum of powers such that the coefficients are eventually 0. So this is just saying coefficients are eventually 0. That's all it's saying. Okay. All right, so let's start with polynomial addition. And if we didn't have this notation, then defining these things and proving properties would be a little bit difficult, as we'll see here in a second. Okay, so given two polynomials, which again we're going to use this new notation, and I'll show you how the notation is helpful. We define the summation of R and S to be just add the coefficients. So since Rk is 0 for k bigger than or equal to something, and Sk is 0 for k bigger than or equal to some other thing, let's set capital N to be the max of m and n. Then Rk plus Sk are both 0 because, sorry, let me qualify k. For k bigger than or equal to n. They're both 0 if you're bigger than or equal to the max. If you're the max, bigger than or equal to the max, and so this defines another polynomial. We would be concerned if maybe the coefficients weren't eventually 0. And so the notation is helpful because we don't have to like say, oh, Rk only has terms up to n, the polynomial for S only has terms up to m, and so we have to decide which is bigger, n or m, and then we can define the addition. There's other ways around this. There's an idea called extending by 0 and infinite tuples. It's another idea that the book considers. I like this part. It's just a formal sum that's eventually 0, and so we can see it be really useful here. In particular, if you wanted to do a quick proposition, for example, like suppose that you wanted to prove that polynomial addition is commutative or associative even. How might you do it? Well, let R and S be as before. Then R plus S is sum of Ri plus Si t to the I. Sometimes you'll put an I down here. And then S plus R, but we've abused notation pretty. This notation is pretty pretty lax, so you don't have to always write the I if it's understood what the index is. And then this is sum on I Si plus Ri t to the I. But we have a field, so the coefficients are in a field. So all of our coefficients are equal. Thus, the polynomials are equal. Let me scroll down a little bit more. Okay, so that proof was very easy because of the notation. All right. So that's polynomial addition, and then we have polynomial, excuse me, multiplication. So polynomial multiplication. Keep in mind that polynomial multiplication is inherently notationally complicated because you have to sort of do distribution everywhere, right? So given R and S as before, I'm just going to quickly write them out. Then R times S is sum on, we're going to use a different index just to keep with the book's notation, Qj t to the j, where Qj is, oops, where Qj is a sum So what we're going to do here is we're going to add up all possible ways that the indices could add up to j. So this can be RH, SI. Now this is not weird. Let me just do a quick computation to see where this is coming from. As an example, suppose you wanted to multiply R0 plus R1t plus R2t squared with maybe some S0 plus S1t plus S2t squared. How might you multiply them? Well, you know that you have to, distribute. So how many ways can we get a constant term? Well, R0 times S0. Notice that 0 plus 0 adds up to 0. The indices add up to 0, and that's the only way to get a constant term. So this is our degree 0 term. How can we get a linear term, something of degree 1? Well, we can have R1t. Let me use a laser pointer. We can have R1t S0, or we can have R0 S1t, and that's it. So R0 S1 plus R1 S0. And notice the indices, they have to add to 1. All right, how can we get a quadratic term? I have to give myself more space here. Well, we can get an R0 S2, an R1 S1, or an R2 S0. That's the only way to get a t squared. So we write that out, R0 S2 plus R1 S1 plus R2 S0. And so on. And you're going to keep going until you get to, let me give myself a little bit of space here. You're going to keep going until you get to R2, I don't need parentheses. The top term in this expression, it could be that R2 or S2 is 0, we don't know. But the top term here is going to be R2 S2 t to the fourth. Notice the indices still sum to 4. They sum to the degree. So in the notation from before, this is like our Q0, this is our Q1, this is our Q2, and so on. We're going to have a Q3. I guess I could have done the Q3, but this is our Q4. All right, and that's why the formula is what it is. It's just all ways of summing to the right, for the indices to sum to the right number. Okay, so this is polynomial addition and multiplication, and in your homework for this chapter, you're going to prove some properties using what we have here, using these defined operations of addition and multiplication.